Good evening, all. I'm extremely sorry for this inconvenience caused and delay because of my some problems at my side. So today I'll be just talking about how you analyze ultraviolet and X-ray data, mainly from AstroSat. I'll be concentrating on only AstroSat data. So before AstroSat, before talking about that, I'll just give a brief introduction to AstroSat. What exactly is AstroSat? How many payloads are there? What kind of data you get from AstroSat? And why we have so many payloads on board AstroSat? That means why we need multi-wavelength, and I'll introduce you to UV data analysis. What are the major things you have to look into, and followed by X-ray data analysis. We'll end with conclusion. Let me start with AstroSat. AstroSat is India's first space observatory dedicated for astronomy, and this was launched on 28th of September 2015. We are in the 10th year of its operation. Even though it was designed for only 5 years, we have almost doubled the time, and all the payloads are working satisfactorily, and we expect it to work for a few more years. So AstroSat mainly carries 5 scientific experiments. What we generally call it as payloads. So covering visible ultraviolet to hard X-rays or high energy X-rays. So almost all of them are realized or developed by different institutes from India, and with collaboration with some foreign countries also. So AstroSat is a real example of multi-institute, multi-nation observatory class mission. AstroSat, as I mentioned earlier, carries 5 payloads. 4 of them are co-aligned, means whenever you do observations from a particular target or a particular field of view, 4 of them will be pointing at the same position. That means that AstroSat is capable of simultaneous multi-wavelength observation from a star or from a cosmic object. So it has ultraviolet imaging telescope, which is a UV telescope. It is a twin telescope. It has 2 telescopes of 40 centimeter apertures each, and it covers a wavelength of 1200 to 5500 angstroms. And this has a very good spatial resolution of around 1.5 arc second. In addition to imaging, it can also do slitless spectroscopy in the photon counting mode. Then the UVAT was made at Indian Institute of Astrophysics, Bangalore, in collaboration with IUCA, Pune. LAXPC is Large Area X-ray Proportional Counter, which is a combination of 3 proportional counters, and this can do observations in 3 to 80 keV. And the field of view of this is around 1 arc minute by 1 degree by 1 degree, which is defined by the collimator. It do not have any imaging capability. Then soft X-ray telescope, which observes the sky in 0.2 to 8 keV, and it has a optics. I'll be talking about optics when I come to SXT. Similarly, we have cadmium zinc telluride. This is using masks, coded mask. It can give imaging in hard X-rays. So LAXPC, soft X-ray telescope, cadmium zinc telluride imager, all the 4 are actually realized at the Tata Institute of Fundamental Research with Raman Research Institute, University of Leicester, and Canadian Space Agency, University of Leicester, and other ISRO centers from different parts of India, mainly VSSC at Trivandrum and Space Application Center, Ahmedabad, along with PRL, Physical Research Laboratory. UVAT, as I mentioned, it is a product of Indian Institute of Astrophysics with the ISRO and IUCA. Canadian Space Agency has provided the sensor required for UVAT. So scanning sky monitor is the only one which is not collinear or which will not be looking at the other direction, is developed at ISRO, that is at URO Satellite Center, Bangalore. So spacecraft and operations and everything is taken care of by ISRO with the ground software from multiple institutes. And to help the people, please remember this particular issue. If you want to actually use the AstroSat data for your analysis and interpretation, we have set up a support cell called AstroSat support cell at IUCA Pune. It will help you in multitude of operations, from writing a proposal to AstroSat. As I mentioned earlier, AstroSat is an observatory class mission, and it operates on proposals. So anybody throughout the world can write a proposal to AstroSat requesting for time, and based on the merits of the proposal, you may be given the time on AstroSat. So to help the people in using the data, AstroSat support cell is established at IUCA. We are from ISRO, and it can help you from writing a proposal to obtain the data, analysis, and even interpretation of data. And we actually conduct multiple workshops throughout the year. As of now, one workshop is happening at Calicut, Kerala. Ultraviolet Imaging Telescope is a twin telescope. It has two Ritchie criterion telescopes of each 40 centimeters. So it, as of today, a whole world, it has the best spatial resolution of 1.2 arc seconds. So it has totally 8 filters in NUV, 8 filters in UV, and visible has 6 filters. So you may be thinking, how come two telescopes are giving three sets of data? So NUV and visible are on the same telescope, and they are split using a beam splitter, and FUV is in one telescope. So I mentioned that it has a best spatial resolution. You see at the top right corner of the slide. So that is the best image obtained by Galax, which is as of now is the next UV telescope available for us. Below that is the same image taken with UV80. You can clearly see the enhanced spatial resolution of UV80. Soft X-ray telescope, unlike UV or visible, photons will not get reflected or reflected by mirror using a mirror. So X-rays are so energetic, they'll simply pass through a mirror or anything. So we cannot reflect back. That means that you cannot focus. So then how do you focus that? We use a methodology called glazing angle. So when you might have, when you are kids, whenever you are near a water body, you might have played a game called skipping the stone. So you just take a stone or rock, and when you actually throw at the water at a very shallow angle, you might see that instead of actually it going by into the water directly, it skips over the water. So I didn't know that there is a world um, cup for this skipping the rock, and the highest number of skips is around 13. Okay. So so similarly, when an X-ray is made to fall on a very shallow angle, very close to 0 degrees, then instead of just going through that, it will get deflected a bit. So using this technique, we can actually bend the X-rays and made to focus on a single point, and hence we get a image. But in SXT, if we simply use a one single foil, then the total effective area, which will be collecting that, will be very less. So to increase the collective area, we use multitudes of such films. So you see on the bottom left. So that shows one portion of the image. And since we need a very fine coating, and also we need very high Z material for reflection, we use gold for the foil. So then comes large area X-ray proportional counter. Proportional counter is not nothing but a wire stretched inside a gas. When the X-ray photon falls on this, so this X-ray photons releases electrons. So then these electrons are getting multiplied with the potential difference in the gas, and gas multiplication happens, and we can actually finally detect this photon. So the number of electrons ejected or number of electrons collected will be proportional to the initial energy of the X-ray photon, and hence it is called proportional counter. So one such cable is not enough. So we use multiple of such multiple such wires, and together they call it as X-ray proportional counter. You can see the size of an X-ray proportional counter, one such unit around which people are standing. So three of them combined to give you around 6,000 square centimeters of collecting area, and it was the highest collecting area when it was launched. So this is it uses a gas called P10 gas, and you can actually measure up to 60 kV using this. I told you that X-rays cannot be bent by this mirror. We use a glancing angle or glazing angle, but at high energies, even this will not help, because the high energy particles will simply pass through that. Then we don't have any other option of imaging it. Not true. What we can do is, all of you have seen IPL matches, right? Most of the IPL matches held during the night, and so they'll be using multiple light sources or light bulbs and etc. So whenever you see a person walking around, you can clearly see that he will have multiple shadows. So by looking at those shadows, we can say where exactly the source is, light sources, how many light sources are there, and which angle and everything, right? Extending the same principle, we can actually define a alternate, not alternate, a set of open and closed elements, where closed elements will stop the X-rays and open elements will allow to them. Using this mask, we can actually uh, image the sky in very hard X-rays. This method is called as coded mask imaging, and whatever that you can see one such mask available on the right side. So then these coded mask photons are made to fall on the pixelated image, a pixelated array, and with this one, with some technique, we can actually detect the images. We can make images. So with this, we can get angular resolution of around 8 arc minutes and energy resolution of around 10% at 100 kV. You please note that cadmium zinc telluride image sensors are capable of measuring photons up to 250 kV, but imaging is possible only up to 100 kV, beyond which the entire collimator will act like a open collimator without any collimator, and the mask will also not help. So this, even though looks like a drawback, but this is actually is a very good boon in disguise. The way we say that now it acts like a whole sky monitor because it is an open detector now. So this also helped in actually understanding and studying several hundreds of gamma ray bursts. So this is gamma. This also acts like a gamma ray burst monitor, and at the same time, even though it is not designed, it is designed only for imaging and spectroscopy and timing. So another thing was another pillar was added to this, that is called polarimetry, X-ray polarimetry. I will talk about in the last if I have some time. So scanning sky monitor is developed at IIRS. It is sitting on a rotating platform which gives you the full sky coverage. Since I'm not going to talk about the data from scanning sky monitor, which is mainly used for a user and alert, I'm not going to talk about that data, hence I'm skipping that. So comes to why multi-wavelength. Almost all of you, I think, are familiar with this image. So this is the image of an elephant as described when a king asked some 5 blind people to describe an elephant. Each one touched one part of the elephant, and he described how the elephant feels like. The one who touched the ear said that it is like a fan. The one who touched the trunk said that it is like a python. So like that, each one actually said that, okay, the elephant looks like this. But the question now is, who is correct among them or who is wrong? So none of them is correct, and at the same time, none of them are also wrong, because whatever they explained, whatever they actually defined the elephant as, is what they could actually perceive. Okay, with their whatever the sensor sensitivity they have. Only you get the full picture of an elephant only when you combine the inputs of all of them. Why am I telling you this? So this is the first picture taken by Rontgen. Okay. So when he took this picture, then it opened a new avenue for medical field, because till then, if you want to know whether the inside of the body something is happening, like a bone is broken or not, there was no other way other than cutting it open. But with the invention of X-rays, we could, without actually cutting the body, we could actually identify what might be happening. So it gave a completely different window for us. So continuing on that, entire electromagnetic wavelength starts with radio, goes up to very, very high energy gamma rays. Now consider this. Do you know what is this? This is our sun. So whatever are the black dots on in the picture, it's not a mistake, like it's not a rubbing of something. It is a real feature of the sun. These are called as sunspots. These are the places where the temperature is slightly low, and hence it is slightly less in brightness, and hence looks like dark spots. Now that clearly says that it looks like a black body radiation. But now consider this image taken at the same time. On the left is taken in IR. Now there is a problem here. Even though the spot looks darker, it is bigger in size, okay, compared to optical. Below on the right side is taken in UV ultraviolet. Now we have a real problem. Whatever were spots are dark areas on sun now are very, very bright. So that cannot happen if sun was acting like a black body. So something else is happening there. And below that is on the right side is in X-rays. That also shows that something different is happening, because whatever was darker in the visible is now very, very bright in X-rays and UVs and even radio. So similarly, you can say you take this picture. This is a picture of crab pulsar. This pulsar is rotating at 33 times per second. One of the best magnetic dynamo in the entire universe. But if you see that one, to get a clear picture, you have to see that object in all the four electromagnetic wavelengths. So to get an idea what it is happening. So the same picture taken with our UV-AT. So that clearly says that just by observing in one particular wavelength won't help you in getting the full picture of a cosmic object, and hence you need multi-wavelength, and hence astrosat has multi-wavelength capabilities. So let's come to UV-AT first. UV-AT, these are some of the pictures taken with UV-AT. So UV-AT data, now I'm going to data and analysis and other things. Okay, so UV-AT data can be used for imaging and photometry. That is what normally you do, right? You take a good picture of a person, and that is called as imaging. And what is the brightness at each point, if you calculate, that is becomes photometry. So that is the major thing what almost all of us are familiar with when we call astronomy. But in addition to that, it can also do timing. What is meant by timing? I can actually see whether something is varying with time. Is it constant or varying? For example, just look at around you. When the sun is just rising, before the sun rises, the entire sky will be very, very dark. Just when it's rising, it's slightly brighter. And when sun is on the overhead, the brightness will be maximum. And at the same time, if there are clouds, the brightness drops. Okay, so in that way, by actually looking at not exactly directly at sun, just by looking at the intensity of light and other things, you can say where it might be. In the other sense, where you can actually say what might be the time. Okay, so similarly, we can actually study a lot by looking at these objects, how they change with time. And then after, in addition to changing with time, you can also look at how they're changing with energy or wavelength. That is called as spectra. So the UV-AT can give two types of spectra. One is, as I mentioned earlier, UV-AT has a total of 8 filters. One of them is used just to block, so that it is for the safety purpose. And then similarly, NUVA has another 6 filters. Visible have four filters. So if you actually observe the object in these filters, you can make a plot. This is called as a spectrum. This will give you only points. In addition to that, UV-AT also has grating spectra, which gives a continuous splitting of UV light over wavelength. Okay, this is like splitting the white light into 7 Vib-Gaier lights using a prism. Okay, here we use grating to split it much more finer. So how much finer? The gratings have 400 lines per mm. So these are some pictures taken with imaging. Okay, on the right side, the blue one, which is very close to the center, blue dot is a supernova which happened in a galaxy, and this was caught by UV-AT. And I had another image where this was not there, taken before this. I missed that, forget to add that. And the below down is called as atoms of peace. You can clearly see the extension of emission from this particular galaxy. So most of you are aware of imaging. So hence I'm not going to talk about imaging. Just before that, I will say how exactly imaging is done. So in UV-AT, unlike optical, the light cannot be measured using a CCD or something. Because of this, what we do is we made the UV light to fall on photocathode. These photocathodes generate electrons. these electrons are made to fall on fiber optics. Okay, so these fiber optics actually acts like a photometric. When it is actually falling through the fiber optics, it actually hits the walls and then generate more and more photons. Okay, more and more electrons. Okay, and then these electrons are made to fall on another sensor to create more photons. So finally these photons are measured using a CMOS sensor. Now the problem is these whatever the fiber optics style type of photomultiplier tube, whatever I mentioned, they are not made straight. So initial part of the focusing is slightly bigger than the final sensor part. So hence they are actually made like a cone shape. But when we are trying to make it a cone shape, it will not be perfectly one-to-one match. So there can be slight discrepancy. Because of this, wherever the photon we are expected to fall may fall at a slightly different place. This is called as distortion. Okay, so we have actually I have worked. Sorry to say I am just talking about myself. So this is it gives you a way of how the distortion is happening. So by by actually correcting these distortions with lot of simulations and calculations, etc., we could reach 1.2 arc seconds. Otherwise, without applying the distortions, the resolution is of the order of 3 arc seconds. Okay, and the right is one of the galaxies used for finding the distortions even on board, like when in the sky. So these UV, unlike CCD and CMOS, can measure individual photons. All these photons are combined on ground, and when they are doing like this, there can be a drift. Means the satellite will be looking at one point, but it can be actually, you cannot actually keep something very stable, right? Then it can be slight movement of the satellite. So this satellite is actually corrected, and which is called as drift correction. And after that, finally background is corrected, subtracted from this image to get a final image. So UVAT imaging is by in this way. And we actually try to measure, we take a particular position of the UVAT image, and then from that, if we actually calculate what are the number of photons or the number of counts in that particular area over time, we can call it as and convert that into, sorry, take photons in particular area and convert that into magnitude, we get photometry. So this is about imaging. So you can, on the right side, bottom right side is the PSF, peak spread function. A single photon or a photon, because even after all these corrections, there will be a spread in the photon. Instead of a point source, a point source can actually make a slightly disturbed this one. You please remember, when I talk about SXT, we will actually be talking about a different way of point spread function. Okay, so on the right side shows it spreads over almost 9 pixels instead of falling on a single pixel. On the left side, it is a different galaxy taken in one of the filters, FUV filters at 141 F154W. So you can clearly see the variation in the images. So this is about imaging. And coming to timing, as I mentioned earlier, so at each and every position, whatever the way that photons are, sorry, flux or the counts are varying is called as timing. And how do we do this? We do use a tool called curve fit. Okay, so this curve fit, all you need is to give the data from UVAT and then select the targets or positions from where. Can you see on the left bottom left? So can you see there's some bright object and smaller objects and etc. Now you define certain regions of the image and tell the curve fit where are all these sources are there, from where you want to actually extract counts as a function of time. So counts as a function of time is called as light curve. All these 6 positions, so from that, how the counts are varying is given in on the right side. The top bottom, sorry, the one which is on the right side, second one, so which shows like a dip now. I'm sorry, because I'm using the laptop in online mode. I don't know whether you are able to see my mouse or not. Okay, So this particular position is actually corresponds to this light curve. So you can clearly see that there is a very change in uh, counts for some reason. So what is that reason is actually the science. But compared to that, if you consider the other targets, it is this kind of variability is not there. That clearly shows that it is not the systematic variation, but it is actually the variation because of the source itself. So that means that we are getting some information out of the source. So then use this information to calculate whether this variation is periodic. So then you can actually run a Fourier transform, or is it not periodic? So like this, all these things you can actually do with that. And with this, you can do a lot of science from that. So just to talk about some science, what you can do is, so coming to our solar system, one American astronomer, she has actually observed Neptune, and she found that there is a dimming of light from Neptune over periodically. So with that, she could actually able to show that this dimming is now happening because of clouds. As I mentioned in the first, whenever there is a cloud, the sunlight will reduce. It will become darker. Similarly, there was a dark because of the cloud coming over, so there was a dip. With this, she could actually calculate the velocity of wind because these clouds were moving. And she found that the velocity of winds in Neptune is almost 1,200 kilometers per hour. That's the kind of the speeds which the wind speed is there on Neptune. All this was done only with this kind of light curve. So then how do we discover? So you know that there are thousands and thousands of exoplanets currently discovered. As of last month, it was around 6,000 plus numbers. And how does all these things are discovered? One methodology is to look for radial variation. Another one is to look for continuously looking at a star and see whether there is any periodic dip. So whenever a planet comes in front of the star, its intensity decreases because planet will cover a portion of the sunlight, right? When I say sunlight, starlight. Okay, so in that way, if there is a periodicity, you can actually calculate, you can identify whether it's a exoplanet or something else. So the width of the dip tells you what is the size of the planet, and using other techniques, you can even say how far it is from the star and all sort of things. So this is one of the methodologies to study exoplanets. So like this, there are multitude of users. I mentioned sometime back that the crab pulsar. I'll talk about crab pulsar later. I mentioned about crab pulsar. I told you that it is rotating 33 times per second. How do we know? With the same sense. You just keep on observing it and see how the photons coming from that one varies with time. Okay, with all this, and then with that, they could actually identify it as a neutron star. So in this way, you can do a lot of science using timing. Then comes spectroscopy. I mentioned about variation of flux with time as light curve. Similarly, variation of flux with wavelength of R energy is called as spectroscopy. And in the middle of the slide, so it shows this is using grating spectra, grating. Okay, so when a star or a cosmic source is observed, if it is a point source, then you can actually see that the spectra is split into orders, different orders. On the right side is plus, and the middle one is a zeroth order, where without any change, whatever the photons comes, they will come there. Half of the photons will be in this zeroth order, and the remaining will be split over the multiple orders. So on the right you have +1, +2, and on the left you have -1, -2, etc. So in the same, and this is left is on the for the NUV, and the right is for the FUV grating. And this is about a point source. What happens if it is an extended source like a galaxy? You can clearly see the image of a galaxy taken in UV80 and the same image taken in grating. So this will split. So what will happen is it may become difficult to actually separate out two sources from whose spectra might be overlapping. Okay. Now, after this, so we actually what do we do is we do something called as calibration. What is calibration is, so each wavelength will be to ideally we want each wavelength to fall on a single pixel, but for with depending on our grating and other details, it might happen that more than one wavelength will be falling on a single pixel, because our pixel is a least sensor size what we can separate from the other one. So we calculate the distance from zeroth order where actually these photons are falling, and this distance is actually calibrated using a known source, so that we know that if it is falling at 100th pixel, that means that it is around 1300 angstroms. If it is falling at 150, it is going to be 1400. Please don't take that this is not the exact numbers, I'm just giving you the some numbers, some idea. So like this, we can actually calculate at what is the wavelength at individual pixel from zeroth order, and then we can convert then into wavelength. So when we plot that, we'll get a big image like below. So this is how the flux is varying with wavelength. So that shows a lot of things. I'll tell you what exactly in the later case. And the same one, when it is converted into first top is a pixel number, and when it is converted into wavelength is shown in the bottom. So what is the use of this? You see on the right. So by actually seeing the spectra, we can actually make up many things. One of them is whether it's a black body radiation or this one. Most of the times in X-ray what we do, but we can actually find out the whatever the kind of elements which are there in that particular object. For example, if it's an exoplanet, we can tell what are the objects, what is the environment of the planet consists of. So we can identify the major elements and etc. by actually seeing that what are the elements we can see in that one. Okay. So in the top bottom, you can see silicon, you can see ferrous, iron, and all sort of things. So with that, we can actually talk about what is the kind of environment it has. So similarly, we can see some for some other source, NGC 7469, another spectra is given. So using this, we can actually characterize the object. So just the bottom plot is just to tell you what it is. So this continuous, whatever the red line is there na, on the right, that is the spectrum from grating. And you see this red green dots. These are all what we call it as filters. So using the filters, we could actually done this one, but it would have given a very sparse data. So modeling would have been tough. Okay, that's about UV-AT, imaging, timing, and spectroscopy. UV-AT is slightly straightforward. We don't have to worry much about UV-AT. But when we come to X-ray, we have to think completely differently. The reason I'll talk about it. So as unlike in visible, where we measure the total flux in a pixel, because the number of photons will be very, very high. So in X-ray, the number of photons are minimal. Okay, so individual X-ray photon can be measured. So not only just measured where it is falling on the pixel detector, we can even actually measure when exactly it is reaching the pixel or detector. And then we can actually measure the energy of the individual photon, and even polarimetric way in which direction the polarization angle is there. All these things. So all the four pillars of astronomy can be done with X-ray data. So first one, since we know where on the detector it is falling, and if we are using a optics like in SXT, so with that we can get a direct image, or using a coded mask we can get images, coded mask images also. And since we know each and every photon when it is reaching the detector, we can use it to construct the light curve analysis or the timing. And also since each individual photons energy we can measure. Okay, so when we plot as a function of energy, we'll get a spectra. So polarimetric information. So from a single method, we can get almost all the information available on that. How to utilize it is left to you. Okay, so coming to imaging, you remember, we go back to my initial comments about SXT and this one. So this is on the top is SXT imaging. It is almost like a optics, which is called as grazing optics, and the bottom one is a coded mask. So in the middle image actually shows the image from one of the targets. So please see here that the point spread function is not uniform here. It almost have a like a structure. Okay, it almost looks like a cut cross. So this is, and when you want to come take the data, you cannot actually leave out the photons. Already I said that number of photons coming from X-ray sources are very minimal. In that one, we don't want to discard multiple photons. So we cover a very large array. And the four bright spots on all the four corners are calibration sources to actually calibrate the energy of photons. So just to give us a comparison, on the top is from Chandra. This is an X-ray image, and compare that with a UV-AT image. So X-ray image can also have very good precision, but then you have to have spend lot of effort to make a optical X-ray optics. So we are going for some similar ones which can be easily made on ground, which is, serves our purpose. Okay, so the imaging is then once you get the image from an X-ray source, so we can actually continue like anything like the way we have analyzed visible or UV data. So I'm not going to talk much about it. So getting up to imaging is the major part. Here we'll not have any background information, background data. What most of the times we use is in the same image where there are not many target sources, we take that area to calculate, approximate, estimate the background, and we use this as a background, use this for background subtraction. So then comes timing and spectroscopy. Just bear with me for a minute. Earlier, when I was talking about UV-AT, I talked about timing first, then went to spectroscopy. But I am going to change that here. The reason is, I'm sorry, can you just get some water? So the reason for this is, so in time, when we are doing timing, there in UV-AT and others, the timing was done using filters. But since there are no such filters here, we have to filter on the basis of energy. But how do we know the energy of each photon? So to estimate that, we can actually estimate, but I'll tell you about spectroscopy, where I will talk about how individual photons energy is defined, and then come back to timing. When you take when you observe a X-ray source with any detector, for example, it might be LAX PC or CZT or any SXT. I told you that individual energy of each photon can be estimated, but we cannot directly estimate that. So what we get is a pulse height invariance. So that means that it might be falling on one particular pixel, from which we can actually estimate what might be corresponding for energy of the photon. So we split that into channels. So now in UV, when I was talking, the distance from the zeroth order, the pixel defines the wavelength ratio. What it will be energy or wavelength of that photon. But in X-rays, it's not possible. There is no grating. Some detectors use grating. For example, XMM Newton and others. Chandra also has a grating. But in our Astro set, we don't have X-ray grating. So all we have is certain with its energy, which it will fall in different channels. Okay, so it is like sieving. When you are doing sieving, the ones which are very small will fall first, and ones which higher sizes will be floated on the top only. Like that, it will be falling on different holes or different channels. How do you convert this channel? Before that, when a X-ray photons interact with the detector, it might be a gas like in LAX PC or in CZT or something like that. So it won't actually transfer its entire energy to the detector. So this energy can be split into multiple physical processes. It can give out some energy in the form of fluorescence. Fluorescence, you know, right? When you actually whatever, some of you might use a watch where in the night it starts glowing. So whatever the energy it has absorbed in the daytime, it emits in the night. That's called as fluorescence. So like exactly like that, a portion of that energy can be given out as fluorescence. and some of portion can be given out as escape peak, where it is very close to the transition energies, and then it can be a photo peak, where most of the energy of the X-ray photon can be converted into electrons, and they can be given out. So it can be either escape energy plus the energy, kinetic energy of the electron, which will actually further ionize the photons, and so you can get a energy. So if you want to actually calculate the energy, and see, and the bottom is pulse height, pi. So this is actually varying. Let me use my mouse. Okay, see this bottom, you can clearly see that each energy is falling at a different channel. So a single photon is giving all these effects. Now, how do you calculate the what might be the energy of the total energy? For that to do, you have to sum all of them. Okay. So how do you know that what is the probability of each energy giving? Say, assume that there are two photons. One is at 1 kV, another is at 5 kV, and the third one has 10 kV. All the three will not give the same type of spectra, means same type of effects. So the 10 kV one might dump more for fluorescence and more at photo peak than escape peak. 1 kV can do less of more of fluorescence, less of photo peak, like that. So you have to actually calculate at each energy level what is the probability of um, flux coming from coming at each of these different physical processes. So then you combine them with the probability to get an energy of the photon. Okay, so all this information is required if you want to convert this channel into energy. That is done using what we call it as um, response matrix function. So response matrix function says that if you throw a photon at that, and if you tell what is the photon energy, then it will go back and actually calculate and see the probability and everything, and it will tell you what is the total energy from that one. Okay, so then there is called as ancillary response function. So there might be some deviations from the response matrix function. So this will correct the normalization. In addition, so then by correcting all these things, you then apply the photon PA channel on the left top, and then when you apply the response matrix function, then it will be converted from channel to photon energy. Can you see the difference between the leftmost and the middle portion? So here what happens is, many times it so happens that the number of photons are less as you go higher and higher in energy. So we have to do lot of things, like we bin it. So we bin it such that multiple number of photons will there will be minimum number of photons on each bin. Otherwise, what happens if we are talking about only one photon in each bin, then the statistics will be very poor, because what we call it as low number, whenever there is a low value, so the errors will be more. Okay, so that's why we bin. And then on the rightmost, we are showing two spectra, one from soft X-ray telescope, which is going from 0.5 keV to almost 10 keV. Another one is large area X-ray proportional counter, which goes from 3 to 80 keV. Now these two will have their own interactions. They are not the same detectors, so hence the interaction will be different, and then our same photon of same energy, whatever it is producing, number of electrons and other things will be different. So to match that, we might have to use what is called as normalization. Okay, with all these things, we can actually model the spectra. From the modeling, we can see what might be the nature of the source. Okay, so if you consider this, and I'm just giving an example. See, at around 6 kV, between 4 and 10 kV, when we actually fit a model, there seems to be some excess left over there. Okay, the model is unable to fit that. So that corresponds to a iron line called iron K alpha line. Okay, this is a fluorescence line, and unless and until you take that also into consideration, your model will not be proper. Okay, like this, each one will tell you. And the whatever they have used is disk black body. I'm taking just an example. And so if you see the total model, there is a absorber. So what is this absorber do? You know that whenever you are seeing, whenever sun is just rising or when it is setting, you can directly see the sun. But when it is exactly overhead, you cannot see the sun because it will be very, very bright. What's the reason? The reason is called as absorption. Okay. So in optical parlance, we call it as extinction, because some portion of the light will be absorbed by our environment, means our atmosphere. So because of that absorption, it will look like very, very faint, and hence we can directly see that. But when it is above us, the amount of atmosphere height which goes the light goes through is minimal, because you are seeing almost directly, and hence it will be very, very bright. Similarly, we are talking about these cosmic sources which are very, very farther away. In between there can be a lot of material, for example mostly hydrogen. So we each direction can have different hydrogen content. These hydrogen different elements, and we actually consider all of them as hydrogen and equivalent hydrogen. We call it as equivalent hydrogen density. So this hydrogen can actually absorb certain portion of photons, mainly in the soft X-rays. Okay, that is we call it as black body absorbers. And then what is disk black body? Disk black body is, black body radiation. It looks like a bottom down, but in most of these binaries, what happens is the amount of matter when it is falling onto the object, it actually emits X-rays. But when this matter is falling onto that, it will not fall directly because of the conservation of angular momentum. It will start going around the central object, compact object. It can be black hole, it can be white dwarf, or it can be neutron star. So then this will form a disk, very thin disk. So ones which are very close to the compact object will be at a high temperature, where ones which are away from that will have a lower temperature. Now, if you try to model this entire thing with one black body, then it will not fit, because it cannot fit either the ones which are very close to the body or ones which are much farther than the body. So you have to split or divide this disk into multiple parts, and each one can actually be treated as a single black body. So the sum of that will give you the total disk black body, that we call it as disk black body. It's a difference is black body and disk black body is, disk black body is more number of black bodies. So with these two, we can almost model the emission or the spectra of this particular object. That clearly shows that it is emitting almost like a black body. And then comes, so still there is one more component. That component, to actually explain that component, we need one more Gaussian kind of this one model component. So that means that there is a line emission also. Okay, like this. Just by looking at it, now we got so many information about that object, right? So we can even say what is the amount of absorption between the source and us. In addition to that, what is the emission, major emission, that it looks like that is black body, and in addition to that, there's a line also. So just by looking at one spectra, we can get many such information. This is what interpretation is. So this is what X-ray spectroscopy can teach us. Okay, these are the kind of information X-ray spectroscopy tells us. What is the maximum temperature there? What is the minimum temperature there? Whether there is what kind of material is there, and whether there is a fluorescence, etc. like that. So then comes timing, because I mentioned in the beginning, so if you want to split the, if you want to take the light curve, you just take all the photons coming in per bin time. It may be 1 second, 10 seconds, 100 seconds. You just bin all of them and plot it on the right side, and you get what is called as light curve. Okay. Now this light curve, you fold, if you know already that this particular target is going around, it has a variability of this much and it is periodic, then what you can do is you can start folding on the same period. So on the left side is crab as such pulsar. Okay, so you can see that 0 to 1 is one period. It shows two peaks. Okay, now you recall that image of the crab. It almost looked like a top, and the emission was coming from two edges. So you can clearly see that it has two peaks. That means that emission is coming from two edges. That means that it is rotating such that both the edges are coming towards you at an angle, because both of them are not at the same level. That clearly shows that one is very much close to you and another one is slightly away from you, means in an angle, different angle, so that it is. So in this way, you can learn a lot of things. Coming back to the colored picture on the bottom right, see here, I am taking the same light curve, but now I am splitting that into different energies. Okay, so the bottommost like 3 to 5 kV, 5 to 8 kV, and like multiple bindings. Now you know why actually I talked about spectroscopy and then came to this one timing, because now if I want to split, I have to tell the routine to choose from between these two energies only. But the data will not have any energy information. The energy information will come only when we apply the response matrix function. How will the program know that? For if I say 3 to 5 kb, how many channels it has to take? That's where you have to calculate. You say that 3 to 5 corresponds to say 100 to 200 channels. Then 5 to 8 corresponds to 200 to 250 channels. Please don't take these numbers as wordsmith. So these are just, I'm just throwing the numbers like that. Then I can say that you collect all the X-ray photons falling between 100 to 200 channels, then that corresponds to 3 to 5 kV, and then bin it in time. That will give you a light curve at one energy. Like that, multiple energies. Why do you need that? You can clearly see that it is not the same. So it is varying with energy also. The structure, if you see 3 to 5 kV, it has only one peak, whereas 8 to 12 and 12 to 10, it shows different two peaks. And also even among them, it's not the same height and same place. Okay. Forget about 5 to keV. If you see 3 to 5 keV and then the maximum energy 12 to 20 keV, the peaks are not at the same time. So that clearly shows that there is a delay. That means that from the same source, it's not coming from the same position. Something is coming later than the other. So why? So like this, you can start actually getting more and more information by looking at it. If it is rotating periodically, then it will give. If you see any periodic variation, then the first chance is there may be some rotation there. Something is rotating, and hence that period is seen here. Then if there is a lag in the between two energies, that clearly shows that the emission position is different. Like that, you can actually start constructing what the cosmic source may be by looking at the timing information. Okay, so in that way, imaging will tell you some details, timing will tell you some more details, and spectroscopy gives you much more information. So by combining all these things and put it to that one, we can actually talk about sources which are billions and billions of light years away from us. Okay, so this is all about UV and X-ray data analysis and what are the basics of that. I can't actually teach you each and every step, and one hour is not enough for that. We actually conduct multiple workshops every year. Okay, so you can join one of them if you want to learn more. And we also have hands-on sessions so that we will teach you how to download the data, how to analyze the data and everything. Okay, before closing, I'll tell you about this is whatever I talked about earlier about is a periodic variation. What if it is not periodic? Something called quasi-periodic means the frequency is not fixed. It keeps on changing with time. Can you imagine? It is not frequency, it is not same, it is changing with time. So if when you actually plot this, you see something like this. This we call it as quasi-periodic oscillations. So these quasi-periodic oscillations, as the name suggests, is not perfectly periodic. They are aperiodic. That means they are evolving. The frequency is changing from 1 to 5 hertz, as and this one it is moving. So with these things, we can actually understand. These are mainly seen in black holes and neutron stars, and we can actually using this, we can talk about what is the rotation of the black hole, what is the rotation of the neutron star, where up to where this one is going. So the disk is going up to where, or where it is falling onto the object, and all sort of things, including sometimes mass of the black holes can be extracted using this kind of data. So I talked about timing, I talked about spectroscopy. Now I'll talk about spectro timing spectroscopy. Okay, so now you take certain observations when there is going to be burst. Okay, these are a very high counts are called as burst. So take only spectra from that area, and then take the spectra when there are no bursts by quiescent stage. So then when you actually when you see the spectra also can have different uh, mm, what should I say, different kinds. For example, in some spectra, the soft X-rays may be more than hard X-rays. In some of them, hard X-ray photons may be more in number than soft X-rays. Some may be equal. Like this, you take multiple types of spectra. In the same spectra, it can happen like that. So then each can happen whenever there is a burst and whenever there is no burst. So compare all these things and plot. So you get multiple ways of plots, and looking at that we can tell what exactly is happening when it is not doing anything, when it is in present state, what the source looks like. When burst is there, what exactly is causing the burst and how long it will stay, and what may be the process which is giving out like this. So like this you can learn many more things like that. On the top, now I'll come back to this top one only. So this is from a it's a neutron star binary. So what happens is, in a neutron star binary, the binary matter is accreting matter onto that. So at some point, the weight of the matter which is falling on as a heap, the weight there may reach to the level where there will be sudden nuclear fusion starts. It's like a atom bomb. In Deepavali, you actually burn these crackers, no? So the atom bomb, what happens? You put a fire, when you light the cracker, then it suddenly bursts, means breaks. So like this, when nuclear fusion is ignited, the matter is thrown out, and this gives lot of X-rays, and that is seen as a burst. Then again it goes back to its original condition. Once all the matter is burnt out, again it will not have enough fusion to go. So then it will start go back, and then again it start accreting, and then again it repeats. Now the question is, this plot is very important, because we have seen within few hours multiple such bursts. So that gives us a idea of what is the rate with which matter is falling onto the compact object. Okay, like this we can learn a lot of things by using most of this information. So even though AstroSat was not designed for this, AstroSat as I also gives you X-ray polarization measurements. So what is happening is, X-ray polarization measurement is the the vector will be in only one direction, is called as 100% polarization. You might have seen many of these specs, particularly uh, what is your Ray-Ban, they come with P, polarized. So if you use a polarizer, then it will actually cut off all the other directions except allowing only one particular direction. With this, you can actually get rid of lot of reflections. Okay, that's only one example. Similarly, many other such things are there. Our TV and our mobile, whatever the light which is coming out, is mostly polarized. So if you have any of you have a polarized Ray-Ban, what you do is you just take it and rotate on top of the screen, LED screen, and you see that at one point it completely blacks out. So that means that is the angle in which the pollution is in the other direction. Okay, like this. So I just, for completeness, I have mentioned this. We have seen from the Crab pulsar polarization not only when the beam is towards us, in the other side, in the non-beam position also. This is one of the major results from AstroSat. Okay, so in one plot, if I want to in one slide, if I have to summarize, so you can get UV imaging, you can get UV light curve, spectroscopy, and Crab, coming back to Crab, it is rotating at 33 times per second with a long observations. Professor Dipankar and others have measured how exactly they're spinning down. Why it's spinning down? Because it's giving out energy. Where is that energy coming down? Coming from? By actually slowing down itself. So they have actually calculated the precise spin down frequency of Crab pulsar. And so on the top right, see this entire, all the images or images, plots, everything is from one target, Crab. Okay. On the top, you have light curve, sorry, pulse profile of crab in UV and in UV, NUV mainly. And the bottom you have pulse profile from different detectors. Bottom most is SXT. The middle two green and pink are from LAX-PC, and the top blue is from cadmium zinc telluride. You can clearly see a lot of variation. Initially, actually, if you see in the low energies, the first peak is larger than more than the second peak, whereas in the very high energy 80 to 250 kV it is reversed, and 32 to 80 kV it's almost equal. So why it is happening? What is what is actually taking away the photons at a lower energy, and why not at the other peak? So all sort of things can be measured using this light curves. And the spectra is also shown on the left bottom most, and it has a coverage of 1 to 100 kV. You can see that it's almost flat. So because why it is almost flat, that clearly shows that it is not from black body, it is something else. It is a magnetically powered rotating pulsar. And also in the middle you have polarization information. So entire astrosat, what it can do, some of them is given in this slide. Okay, so now after all these things, where do I get the data? So the data is available at Astro Browse. It is hosted at Indian ISSDC Strack in Bangalore. So all you need is a email to register in this portal. Once you register, you can download the data, what archival data, any data what you want, and then you can. There are also many links where you can learn how to analyze this data and other things. And if you still have problem, you can actually connect to Astrosat Science Support Cell, which is actually run by ISRO at Ayuka, Pune. So they will help you in all sorts of analysis, data downloading, reduction, interpretation, and everything. Okay, we do conduct workshops also. You can actually keep looking into our announcements, and you can join for these workshops to learn how to analyze the data. So before ending, I just want to show this image on the left picture. This is the image taken by JWST, which is 6.5 meters and which is the costliest costliest mission in the world as of today. Okay, so that image, the green and the green color or the slight blue is from JWST, whereas pink and red is from UVAT data. You can clearly see that. So UVAT data very well complements JWST IR data, infrared data, and is it at par with JWST. I'm very proud of my AstroSat. Thank you.